Everyone. Welcome to this second installment of the Rockham Lunch and Learn series. My name is Zach Resch. I will be your host for this call. If you joined the March Introduction to Portable GPU Programming call, thank you again for coming. This call is going to focus on profiling and performance for AMD CDNA GPUs. We will again be joined by Dr. Joe Schoonover, who will provide this presentation in the flesh this time. You won't be having to watch a recording. So we'll hear from him in just a few moments. But before we get to that, I am going to run through a quick introduction of this platform for anyone who's not familiar. So this platform provides a desktop-like experience. You're going to see a lot of windows open already on your screen. Those can be moved around, resized, rearranged, minimized, and maximized. At the bottom of your screen, you're going to see a number of widgets that correspond to those different windows. I'm going to ask everyone to pay special attention to the Q&A widget. You can use that to ask questions for Joe. And if you do want to ask a question while he's presenting, we have some AMD people in the background to also help answer those questions. So don't feel like you need to hold them. Otherwise, for live Q&A, we're going to get to that at the end of the call. If you need to get in touch with anyone from AMD, you can use the Contact Us button. That's also at the bottom. We have a number of resources available for you in the resource list. They're going to be in the top right of your screen. Some of these will be familiar for any of you who joined last time, but there are also a number of links out to links that you're going to see in some of the upcoming slides. So if you want to follow along, have a look over there and you'll be able to jump out to those links. Lastly, don't forget to provide feedback. Please open up that survey at the bottom of the screen. You can start filling that out at any time during this call. Just make sure that if you do begin filling it out, that you also click submit. Otherwise, once the call ends, all those answers will disappear. So if you have any other questions, if you have any platform issues, you can send a note through in the Q&A widget or refresh the tab if you lose audio or video. Click OK, it will come back and look like it should. So without too much more ado, I'm going to invite Joe up to say hello really quickly. Joe, how are you doing today?
Doing all right, Zach.
All right. Well, I know you've got a lot to cover, so we won't belabor that too much. I am going to bring up a poll. So everyone, you're going to see this pop up in just a second. Again, some of you may have already seen this question, but I am just going to try to get the baseline, see if we've got any updated answers from some of you. So if you have you had experience programming GPUs with any of the following APIs? And you're going to be prompted to select all that apply. You shouldn't be limited there. So click the ones that you are familiar with. If you haven't used it, go ahead and ignore it. I think we are still waiting for couple of answers, so we're going to drag our feet here just a little bit. Joe, what are you expecting to see here? If I can just ask that while we get some people to put some answers in.
I mean, I'd say most of the time I see folks at the moment working primarily with CUDA Open ACC with a few sprinkles in the Cocos realm, which no Cocos today.
No Cocos.
But very cool to see a lot of folks doing OpenMP and HIP already. So should be good.
All right. Well, from there, I will hand this over to you.
All right. Thanks for that introduction, Zach. I really appreciate it. So today, yeah, we're going to be talking a lot about performance and profiling on the AMD GPUs. I did want to make a mention about where a lot of this work is based off of. So I do a lot of work with Pawsey Supercomputing Center. I'm involved in what's called the PACER project over there. And the particular application that we'll be presenting on today for the case study is called IMPRISM, which stands for the Emergent Phenomena Revealed in Subatomic Matter. So I basically did this work with Dr. Wasim Kamla, who's the principal investigator for the IMPRISM PACER project. And I definitely want to give a special shout out to Dr. Deva Deepti Mahanti from the Pawsey team, who spent a lot of time working on this code as well. Just a brief disclaimer, everything here is for informational purposes only. So we're just going to move right on past this. A question I get a lot, and I'm sure it's a question you have already since you're joining here today, is how do we get the best performance on AMD GPUs? Certainly, you're going to have this question anytime you move to new hardware. And my answer to this always is going to be, you cannot optimize it if you do not measure it. So a lot of what we're going to be talking about today is how to do that measuring to guide what you're going to do to optimize your code. There's a basic recipe I usually follow for doing optimization work in scientific codes, which I spend a lot of time working in other people's codes. So this has been a very helpful little model for me to work through. So I hope it helps you down the road. The first place we want to start is to establish a representative benchmark. Scientific codes can do a lot of things. They usually have hundreds of thousands of lines of code. But in practice, you want to make sure that the benchmark problem you're working with as you're porting to a new system is going to exercise the bits of the code that you care about. There are other considerations to take into place here. So usually what we do when we're working on the GPU systems or multi-GPU systems is to start by focusing on single GPU performance before you start doing multi-GPU style work. So depending on where you are in your porting process, it's just important to make sure you have a problem that's appropriate for the goals. If you're starting with initial HIPification, again, start single GPU and then work your way up to the multi-GPU style problems. Once you have your benchmark problems picked out, it's a good idea to start obtaining reference hotspot profiles. Bulk timings of your code can be very helpful because, of course, at the end of the day, when you run your jobs through HPC data centers, what you care about is time to solution. How much time is it going to take? How many resources am I going to use to get my results back? But in terms of doing optimization work, you really want this little bit more of a granular view of what's going on in your code. Where are you spending most of that time? And you don't want to have this hotspot profiles just on the AMD GPUs, especially if you're porting and you already have your code working somewhere else. It's helpful to have a reference hotspot profile on that existing platform where you're running already. And then from this information, you can start to set some realistic goals in terms of what you should be able to get in terms of performance. And so everything we're going to talk about today is going to be focusing on addressing these 3 steps. And usually when we do this kind of work, we do it very incrementally. And I usually follow this very cyclic, periodic process. You start with a profile of your code. From the profile, you develop a plan. From that plan, you implement that plan. You make sure your code is still spitting out the right results. You're getting the performance improvements that you expect. And once you are at that stage, you commit and you rinse and repeat that process until you're hitting the performance goals that are realistic for your application. The application I'm going to be focusing on for the case study, which is going to give you sort of a real world example of how to use the profilers and tackle some problems with memory bandwidth limited applications. It's called COLA. Again, this was from Dr. Wasim Kamle in the Imprism Pacer project. This application, the bits of this code, which is fairly large, that we're going to be focusing on is a section that uses a preconditioned conjugate gradient solver. So think linear algebra style methods, except for the fact that in no time during this code do we ever build a matrix. We're using a matrix-free method, which means that in his code he has functions or subroutines that take in whatever the data is for each iteration and spits out the action of a Laplacian matrix. So again, no, we're not storing dense or sparse matrices here. We're doing matrix-free preconditioned conjugate gradient. Now the type of algorithm that is used for that matrix action it's like a Laplacian. Now the problem he's doing is in 4 dimensions, so 3 in space, 1 in time, and at each grid point in that space-time mesh, there's a vector of data. So it's not just like a scalar Laplacian. So it's a little bit more complex than what you would see in like a mini application or some very simple demonstrative descriptions that are out there in the wild. But the point being is this code's got some nuances to it that are pretty interesting in terms of trying to get the performance out that we want. It's very, very memory intensive. And as I mentioned, this code, we know a priori that it is memory bandwidth bound. From experience of working with stencil codes, this is generally where stencil codes like finite difference, finite volume, low order methods fall. But I will show you today how to use the profiler and some system information to figure out if your code is memory bandwidth bound or compute bound. Now, in terms of establishing the representative benchmark for this code, generally the amount of computational work that we're doing is going to be dictated by the grid size. So how many points I have in the X, Y, Z, and T directions with time in the time dimension. And we are planning in this little project that we were doing, we wanted to start working on the, we started at the V100 GPUs, and the goal was to get that over to the MI100 and the MI250X GPUs from AMD. And the representative benchmark problems that we pick here, since we're doing single GPU, are really going to be governed by picking problem sizes that will fit on the GPU with the smallest amount of memory, because we want to be able to run on all 3 of those GPUs. Because of those limitations, we did think of just 2 problems to consider, like focusing on for doing the performance work. But of course, we, post all this work, we can start experimenting with different problem sizes. So you'll see a lot of references when we talk about the performance of this code in terms of 2 problem size. This smaller one, we'll call it the 16 cubed problem. It's got 16 grid points in the XYZ dimensions and 32 in time. And then the larger problem is our 32 cubed by 64. So small is 16 cubed. The large problem is our 32 cubed. So that's a little bit about the application. We chose the benchmark problem. And in terms of what we're actually solving there, there's just some initial conditions that he seeds in the code. And we have a rough idea of how long it's going to take, starting on the V100s, to run this to get an answer out to get the correct answer out within a specific tolerance. The other little deciding factor here outside of memory, if you're doing this kind of porting work, it's very beneficial to have the benchmark run in a shortish amount of time. Like, you don't want to be waiting hours for a benchmark to run, so that you can then determine whether or not to move on to other steps in your optimization process. So here we're only talking about a couple minutes to run this benchmark, so that we can kind of do a lot of experiments, a lot of code modifications very rapidly. So to obtain the reference hotspot profile, if you're on a system with ROCm installed and AMD GPUs, you can use rocprof, or the rock profiler. The hotspot profiling is enabled by passing the ---- stats flag, and then the other arguments to the profiler are going to be the path to your application, as well as any arguments that you have for your application. The rocprof is going to dump a whole lot of files out of it that give you various views of profiling for your application. If you're looking for hotspot profiles for your kernels specifically, that's going to be in the results.stats.csv file by default. What I usually like to do is download these off the cluster that I'm working on, put them in Google Sheets, Excel, whatever, just, so you have it in a good spot to work with it. And what you see in the hotspot profile, there are 5 columns. You have the name of the kernels, you have the number of calls issued to that kernel, the total amount of time spent, it's going to be measured in nanoseconds, then the average time for each call in nanoseconds. It's really just if you take the total duration column, divide by number of calls. That's what you get there. And then this percentage column. Now the percentage is just the percent of time of all just the kernel executions. It's not measuring percentage of overall runtime or even considering like memory copies. Now, if you are interested in knowing more about the memory copies, there's a similar file. It's results.copystats.csv. It has same kind of layout, except it's going to have the different memcopy API stuff and things like that. But we use these kernel hotspot profiles to kind of narrow down where we want to spend our time optimizing the code. You don't want to be working on kernels that take up only 1% of your runtime if you got something else that's, like in this case, taking up 20%. Now, in this case, for this code, there are 4 kernels that are roughly about equal importance. And thankfully, each of these kernels, they do have a similar memory access pattern. They have similar, computations that are happening inside of it. So when I present all the profiling and performance tuning results, though, we're going to be focusing on this very, very top one, this EO Clover FBC GPU. But a lot of the modifications we make here do end up trickling down to these other 4. Now, relating this, to the things that you might do, it's very often the case you'll find a handful of kernels that you ought to be spending time on. where you're really trying to tune that work down. So this is a really good way to narrow down specific lines of code, specific kernels that you should spend your time with, rather than, you know, tackling all hundred thousands of lines of code that you may have. So we have our hotspot profile. Now we did also do the same thing with nvprof on the V100. So I've got two tables of results here for you. On the very top, we have the small problem, our 16 cubed by 32 problem. And on the bottom, I have the 32 cubed, our large problem. Left is the runtime, the average runtime measured in milliseconds on the V100 for each of those four kernels. And then on the right is the MI100 runtime. And this is really to motivate why we want to spend time doing this optimization work. Is this particular code much like a lot of codes I see, is they have been very well optimized for NVIDIA architectures. They do the HIPification process, and as you could see, you know, over here, like for our smaller problem, we have 0.126 milliseconds for EO Clover FPC GPU, and then on the MI100, we're running 2 times slower. And we see the same thing, similar behavior for the bigger problem. And again, this code was really well optimized for NVIDIA GPUs. We've HIPified and done nothing else at this point. So we need to figure out how to tease out this extra bit of performance by taking into account some of the differences between the NVIDIA and AMD GPU architecture. But at the very least, this tells us, at least it tells me that we know that the MI100 GPUs have a higher memory bandwidth than the V100s. And the fact that I'm going slower on MI100 suggests I've got a lot of room to actually improve the performance. So there's definitely some potential there for us. So now we need to talk about what is a realistic runtime for that I should be expecting on the MI100. How fast should I be able to go once I've ported over? And this is all the, you know, we want to set a realistic goal, because at some point you'll get some really good gains, and then the gains will start getting smaller and smaller as you're doing this optimization work, and you need to know when to call it quits, so that you're not just spending, you know, lots and lots of human labor to really push, you know, inch yourself a little bit closer. You know, we need to know where that limit is for our performance. And there's 3 questions I always ask myself when I try to set these realistic goals. We want to know first, is the application memory bound or compute bound? This is important if we want to understand the kinds of things we need to change to our code to improve performance. If you know if you're bound by the memory bandwidth or by compute performance, we of course want to know what that peak is. So what is the peak memory bandwidth? What is the peak compute performance for the target hardware that we're running on? Because that's going to dictate really how fast I can really do things. And then we want to know, how far are we from that peak? If we know these 3 things, we can tell ourselves what is realistic here. What can we convince ourselves is a realistic goal to shoot for? Okay, so this is a conceptual diagram of the CDNA architecture. So you have, of course, this big space of GPU RAM, which HBM2 on the MI100 and MI250X GPUs. And between that GPU RAM and those compute units, data often travels straight to the L2 cache, and then from the L2 cache out to the shader engines, and from the shader engines onto the compute units. Okay, now in order to perform any floating point operations, you have to move data from memory onto those compute units. There's just no way around it. Now the question in terms of whether you're memory bound or compute bound depends on how much compute you actually do on that data once you've made that journey. Once that data has moved from HBM2 all the way to your compute unit, are you doing a lot of compute on it, or are you doing very little compute on it? That's what we really mean by, are you memory bound or compute bound? For memory bound applications, what the relationship is here in terms of, you know, what you would expect to get for your performance, the achieved compute performance, the number of flops you can do per second, is going to be proportional to that memory bandwidth. And that constant of proportionality between flops per second and gigabytes per second, your bandwidth, so compute performance to bandwidth, is what's called the arithmetic intensity. This is measured in flops per byte. And that arithmetic intensity is a number that is more of a function of your code. And of course, there's some influence of the algorithm that you're basing your code off of, but your implementation in the code is really what drives that number. To some degree, that number can be influenced by compiler options and things like that, but it's very minor. The biggest driving force behind this this arithmetic intensity, is is the way your code is written. Okay, and the way you might see people talk about this a lot is in terms of what's called a roofline diagram. It's just a nice visual way to see sort of how your hardware imposes limitations on your application's performance, and you can plot on these roofline diagrams where your application sits. And the way this is you look at this is on the y-axis you have the floating point operations per second, the compute performance, and on the x-axis we have the arithmetic intensity. And your kernel, your hotspot kernels, may have some arithmetic intensity, and we want to know, are we limited in our compute performance on the left side of the diagram, where you're underneath that roof, where the compute performance is proportional to that memory bandwidth, and beyond that, at some point, there's only so many flops per second that the GPU can do, right? So there's this transition point where you move from being memory bound to compute bound, and where that happens is really it's a function of your hardware, as well as a function of the type of floating point operations you're doing. So in reality, on the GPUs, you can do 64-bit vector FMAs, you can do 32-bit vector FMAs. You can do matrix FMAs on the MI200s and the MI100s, but you can do matrix FMAs for 32-bit, 64-bit, 16-bit or B floats, and all of them have their own, peak compute performance. So it's helpful to know when you're getting into this realm, you need to ask yourself, am I doing vector FMAs? Am I doing this on single or double precision or half precision data? Because that's going to determine the relevant compute bound peak for you on this side. And what we need to know to determine this memory bound versus compute bound is where this intersection between that arithmetic intensity multiplied by bandwidth line reaches the relevant compute flops per second peak. Okay, so we need to determine that critical arithmetic intensity. So again, that's a function of your hardware as well as the type of operations that you're doing. Now, of course, there are all multiple memory bandwidth roofs. You have your HBM2, your L2 cache. Everything I'm going to talk about today is going to focus on global memory roof, because 99% of the time that I've gotten my hands on applications, we sit somewhere just beneath this global memory bandwidth roof for these bandwidth limited applications. So we'll only be focusing on global memory bandwidth, and then for our problem, we'll be picking out the FP64 peak for this application. But just know that all these choices do influence how you're going to answer this question. Are you memory bound or compute bound? Okay, so let's just recap real quick. So if you want to know compute bound, memory bound, we're going to determine that critical arithmetic intensity. So we need to know the peak bandwidth from global memory, and we need to know the relevant floating point operations per second peak. You take that floating point operations per second peak, divide by that peak bandwidth, that gives you that critical arithmetic intensity. So that's what we want. Then we also need to know the arithmetic intensity of our kernel, and that will tell us where we are on that diagram. So there's two ways to get that critical arithmetic intensity. So we're going to talk about the hardware first, and then we'll focus on your software, how you use the profilers to pull out your kernel's arithmetic intensity. So there's two common ways you can do this. One is using the vendor reported metrics in the white papers that come out with the hardware, or you can use microbenchmarks. The thing I like about the vendor reported metrics is if you just got a pen and paper and you can do a Google search, you can find out a pretty good idea of what that critical arithmetic intensity is. Just keep in mind that the theoretical numbers, both for bandwidth and flops, are not sustained numbers. Okay, so they're theoretical peak based on the hardware design. They are helpful guidelines to understand what you're getting yourself into, but they are going to be a little bit higher than what you're going to achieve in practice with an application that's going to run for an extended period of time. This is why I like to also use a micro benchmark, because just having these two numbers is helpful to make sure that everything's in agreement. Now, just remember, the micro benchmarks are going to be a little bit smaller. And the one I found that has been very useful here is the Mixbench micro benchmark. So you can find that on GitHub on the Econdis developers page under the Mixbench repository. So I'll provide some links on the next couple of slides on where you can see some scripts to use these on systems that have a Slurm job scheduler, which of course you can adapt to your own system. So here's some results here. So I've got NVIDIA V100s, AMD MI100s, and then the AMD MI250X. And then on the left side, we have the gigabytes per second, so our bandwidth. And then I'm looking at FP64 measured in teraflops. We're looking at the FP64 vector FMAs, because Dr. Kamle's code only uses vector FMAs. We're not using matrix FMAs. So that's the relevant compute peak that we're interested in. And what I've got in the two columns on the left for each of these groups, for the bandwidth and the compute performance, we have what's reported in the vendor white papers. So that's the theoretical peaks. And then we have the Mixbench measured the micro benchmark numbers. And as I said before, the Mixbench numbers are just a little bit smaller than the theoretical peaks, but this is to be expected. Now, usually when I'm trying to set a realistic goals, I usually use the things that come out of the micro benchmarks, because they're going to be more in the realm of possibility for my code. And of course, I like seeing a higher percentage peak performance when I'm looking at a code. It feels a little bit better. But no, in reality, this is the realistic sort of upper bound you can expect for that kind of performance. Now, as I mentioned before, why I still believe that, even though the code and its current state, the COLA application runs a little bit slower on the MI100s in its current state than the V100 GPUs, why that is actually hopeful for me is because, if you look at the bandwidth numbers here, if you look at V100 to MI100, we go from 851 gigs per second to just over a terabyte per second sustained. And then on the MI250Xs, we hit, another 300 gigs per second, which is nice. So the idea being that if I can suss out the problem that is causing us to not perform so well, if I'm running on the MI100s, if I transition to the 250Xs, I should also see some performance gains there just from switching hardware. Now, in terms of calculating that theoretical or the critical arithmetic intensity, we have these Mixbench numbers. Essentially what you'll do is calculate, take the T-flops that you have, divide by the bandwidth you've got, and that will tell you what that critical arithmetic intensity is. And so once you have that number, what you really need to do then is figure out where your application lies. There's the two ways to do that. You can use hardware events profiling. So you can use rocprof to get the number of loads and stores measured in, I think in ROCm 5.4, it's measured in kilobytes. And then we can use the flop counters to measure the amount of flops done for each kernel. If you know the number of flops, you know the amount of data that you've had in flight, you can estimate the arithmetic intensity by dividing flops by the sum of the loads and stores. Now, I put an asterisk here on the hardware events profiling because flop counters are not a feature on the MI100 or earlier GPUs. You need to be on a CDNA2 GPU to get the flop counters. Which brings me to the other option here. The other option is to hand count these in your kernel, which if you have some reasonably sized kernels, this is not too bad to do. Okay. Essentially for counting the flops, you just add up the number of additions, subtractions, and multiplications you got going on. And then the loads and stores, everything on the right-hand side of an equal sign is a load. Everything on the left-hand side is a store. Just know what kind of data you're working with so you can convert that to something in the units of bytes. If you want an example on how to do that, you could I highly recommend you check out the GPUopen.com AMD lab notes. There's a few articles from Justin Chang on doing this by hand with a Laplacian kernel. It's very, very helpful if you need to do that on the MI100 GPUs. Now, if you're doing this with the profiler, when you work with rocprof and you want to do events profiling, you'll need to create an input file that tells rocprof what metrics you want to measure and what kernels you want to do those measurements on. So each line you see here in this file, I've called meminflops.txt. There's these lines that start with PMC : these are the lines where you're going to specify the metrics you want to gather. And for each line that starts with PMC, the profiler is going to replay that kernel to gather those metrics. Okay, so in this case, if I had all of these active, that would give me 7 times that kernel is going to be rerun in order to gather those metrics. So keep in mind, this adds some overhead to that runtime, which is, again, underscores the idea that you want to keep your benchmarks rather short, so that you're not having to wait hours for your profiling to be done. Fetch size and write size are the metrics you want to use if you want to get loads and stores. What this measures is the amount of data. So fetch size, for example, would be the amount of data loaded from HBM2 memory and into L2 cache, and write size is the other way around. So keeping track of those gives you your loads and stores. And then I've provided some descriptions of the flop counters that you can use for 16-bit, 32-bit, and 64-bit. I believe these slides will be available after the fact, so you guys will have access to that as well. And I'll be providing some links here for how to, from Oak Ridge National Labs site on how to gather those metrics as well. Now, if you want to do the events profiling, once you have that file created, you can pass that into rocprof using the -i flag, I for input, and you can pipe all that output to another file. So you can get, so here I'm just calling that rocprof metrics.csv, which we'll take a look at an example of those files next. Everything else stays the same, so you're still sending it the path to the application arguments. Now, once you get all this data out, of course, it's going to be in a CSV file. There's a few formulas you need to apply to the flop counters to actually get the total number of flops out of there. Again, at that Oak Ridge site, there's a really good example on how to do that. Okay, so we're still asking ourselves, what is this realistic goal here? So remember, we've done some hotspot profiling. We know which kernels to look at. So now we're starting to gather our arithmetic intensity. As I said before, this code did fall in the realm of a memory-bound application. So the metric that we're looking at to establish what is good performance, we're going to be looking at comparing our results. We're going to look at the kernel's memory bandwidth that we achieved relative to the peak memory bandwidth as we measured using the microbenchmark. So what I have in this table is the achieved memory bandwidth for the EO Clover FPC GPUs, so just one of those kernels, for the 2 problem sizes, the larger problem up in the second row and the smaller problem on the bottom. Starting from the left, moving to the right, we have the MI100 achieved bandwidth, the MI250X bandwidth in the middle, and the V100 bandwidth on the right. And just to underscore, of course, we have the run times. We know we're going a little bit slower currently on the AMD GPUs, but now we can quantify this in terms of the performance metric that matters here, which is memory bandwidth. And you can see on the V100 GPUs for our larger problem, we get 85% of the peak bandwidth relative to the microbenchmark. And then on the MI100 and 250X, we're hovering around 36-33%. Now, Dr. Kamle was pretty happy with the performance he's getting on V100s, and since we're able to get that good or that close to that peak on the V100s, it's a reasonable goal. At least in the outset of doing this project, that we thought was like, okay, like if we can get 85% on V100s, we should be able to get 85% on the AMD GPUs. So this would tell us, okay, if I know the memory bandwidth is higher on MI100, MI250, I should be able to run a bit faster on the AMD GPUs, provided I hit that 85% peak bandwidth mark. So that's our goal. Our goal is to get that 32 cube problem to 85% peak bandwidth on the MI100 to MI250X GPUs. Now for the smaller problem, right, the smaller problems typically you're not keeping the compute units as busy. There's not as many wavefronts in flight, and so you don't have as many opportunities to hide memory operations. So, the efficiency there is not as strong, but on the smaller problem, we'd be pretty happy with 65%. Okay. Now, if you are interested, if you check out the PALSI SC organization on GitHub, there's a repository called Performance Modeling Tools. There's a ton of examples on using the mixed bench microbenchmark, as well as some scripts to show you how we did all the profiling for this particular application. So now let's talk about some possible causes of low memory bandwidth. We've given our problem a name. Our problem is we have low memory bandwidth, and we know where we need to go. So the few things I usually look at to start is occupancy. And we'll talk a little bit about that in the next few slides, but essentially the idea is that by not having enough wavefronts in flight, you cannot hide the latency of actually doing memory operations. This is one of the benefits of GPUs, is the amount of context switching they can do by having many wavefronts in flight at any given time. So we'll talk about that in a minute. The other things we want to look at is how well we are treating our L2 cache. If our L2 cache is constantly throwing data out and we're only using small snippets of a cache line, we're going to have some problems. You'll basically be doing lots of round trips to L2 cache. Oh, if data's not there, then we're going to do a trip to HBM2 and kind of waste a lot of time getting data. So we need to make sure, the biggest thing is making sure you have what are called coalesced memory access patterns. So you're bringing in a whole chunks of data that your work groups can use simultaneously, and you're not getting, you want a really good efficiency there. And then in terms of the order of the instructions you execute, so the sort of as you step through your kernel, you need to be careful about the order in which you're accessing data. Most of these systems are designed with the idea in mind that if you touch something in one line, and the next line you'll be touching something in data or in memory nearby. So if you're not taking advantage of that, you can have some poor cache performance, which can really kill your kernel's performance if you're memory bound. Okay, so occupancy is a fancy word for it's really a percentage. It's a measure of the number of active wavefronts on the GPU, and it's usually reported as a percentage. And when we do this, it's going to be the number of active wavefronts we have divided by the maximum possible wavefronts that GPU can support. So the numerator is going to be something that is dictated by how your kernel is written and how you are doing things. The bottom number is going to be a function of the hardware. Okay, so that bottom number you can easily calculate just by running ROCm info. If you're on an AMD GPU, the two lines you want to look for are compute unit. That's going to tell you how many compute units are available on your GPU. And then you want to know the maximum number of wavefronts. This is synonymous with the warps from NVIDIA speak. You want to know the maximum number of wavefronts per compute unit. If you multiply those two numbers together, that tells you the total number of wavefronts you can have in flight at any given time on that GPU. So here's just a reference for you of what that looks like for the MI100, MI210, MI250X GPUs. So the number of compute units from the CDNA series, we had the 120 compute units for MI100. And then as you went to 210, 250, those did get brought down. But you remember the CDNA2 GPUs, they come on these like multi-chip modules. So you have two GPUs on those cards, I guess, except for the 210. The 250s and 250Xs are the ones with the multi-chip modules. But the basic idea, right, is you need to know this number to compute occupancy. And now we're going to talk about some things that can limit the number of active wavefronts in flight. And this all comes down to the idea that all resources are finite. All resources are finite. And the key ones here that you ought to think about is how many registers you have per compute unit and how much shared memory you have. Now, if you're not using shared memory in your code, you can ignore the shared memory roofs, but we'll still talk about them here just in case you end up using shared memory one day. There's two types of registers. We have scalar registers and vector registers. This diagram on the bottom here is just a conceptual diagram of the MI100s or the CDNA architecture for the for the compute unit. So we have, for example, for the MI100s, there's 12.8 kilobytes scalar registers, 512 kilobytes of vector registers, and we have 64 kilobytes of local data share, which is your shared memory space. Now, you may have dealt with register spillage before if you've done CUDA programming, and what that was is if you ran out of register space for your vector registers, some of that data would spill over into shared memory on the NVIDIA GPUs. Now, the difference here is you have LDS, which is distinct from this L1 cache, the 16 kilobyte L1 cache. The way the spillage works on the AMD GPUs is if your scalar registers fill up, they spill into vector registers. If there's no room in the vector registers, they spill to this L1 cache. If there's no room left there, it's going to go to LDS. It's going to follow that hierarchy. Now, in terms of limiting performance, we need to talk about the sort of how resources are divvied up among the threads that are active on a compute unit. Okay. So as I said, there's two types of registers. We have vector registers and we have scalar registers. Vector registers, if you have scalars in your kernel, for example, if you're just, filling out little scalars to hold intermediate results and things like that, those are very likely going to be in vector registers, particularly if those scalar values have a unique value as a function of the thread ID in that kernel. Okay. Most often, you'll see those things end up in vector registers. Like I said before, vector registers are going to spill to that L1 cache, which is also called scratch. Scalar registers is storage for things that are uniform across all the threads in a wavefront. So usually when we talk about scalar registers, we measure them in terms of scalar registers per wavefront. These could be things like the kernel arguments, pointers, anything in constant memory, things like that. And as I said before, SGPRs, so the scalar registers, will only spill to vector. All right. Now, when we talk about things that limit the number of wavefronts the number of wavefronts in flight, we talk about things like pressure. You may have heard the term register pressure before if you've done GPU programming. And all this refers to is the pressure that the finite resources here, the registers, has on influencing the number of wavefronts that we can have. Now, first, I want to talk about the maximum number of registers we can have per thread without influencing the number of wavefronts. So if I know the number of vector registers per compute unit, and if I know the maximum number of threads that compute unit can support, remember we reported from ROCm info the number of wavefronts we can have per compute unit. The number of wavefronts per compute unit is going to tell me how many threads I can have per compute unit. And I know from the hardware specs how many vector registers there are. If I take the number of vector registers divide by the number of threads per compute unit, that's going to tell me how many registers I can give to each thread, and it will have no influence on dropping the number of wavefronts I can have in flight. So we need to know this number. So we get that from hardware specifications. Now, the other number that matters in terms of occupancy is how many your kernel is actually using. So we'll do a quick calculation here in a minute, but the same principle applies for the scalar registers. If I know how many scalar registers there are per thread, how many scalar registers there are per compute unit, how many threads there are per compute unit, I can use that to calculate the maximum number of scalar registers I can have per thread without influencing the occupancy. So we're going to do a quick example to try to illustrate how this works in practice. So let's look at the MI100 compute unit. So the MI100s can support 40 wavefronts in flight at any given time. And each wavefront has 64 threads per wave. Okay, so if I multiply those two together, that gives me 2,560 threads in flight per compute unit if I were at 100% occupancy. And now I have 128,000 vector registers, 3,200 scalar registers. So let's do some math, arithmetic. So if I take that 128,000 vector registers per compute unit, divide by the 2,560 threads per compute unit, that tells me I can have 50 vector registers per thread, and it will not impact occupancy. As soon as I go above 50 registers per thread, it's going to start having influence on the number of wavefronts that a compute unit can actually support, because now you're starting to consume more resources per wavefront. And to be able to serve those wavefronts what they need, the scheduler on the GPU is going to cut back on the number of wavefronts that are going to be dispatched to that compute unit. Same thing for the scalar registers. Let's do that once. We got 3,200 scalar registers per GPU. We've got 2560 threads per compute unit, per compute unit. So that gives me 1.25 scalar registers per thread. Let's convert that to wavefronts, scalar registers per wavefronts, because when we work with rocprof, it's going to be reported in scalar registers per wavefront. So we multiply back in that 64, and that tells me I can have 80 scalar registers per wavefront, and it should not have an impact on my occupancy. So the closer you are to these numbers, the better your occupancy is. Now, I will want to just point out that occupancy is not the end-all be-all. In a lot of cases, it does. If you get better occupancy, it can help performance. But if you've ever worked with like cuFFT or rockFFT, those are really good examples of libraries that have kernels that have very low occupancy, but they have really good performance. So, just take this for what it is. It's a really good guidepost to look at, but it's in some cases it's not the end solution. So now when you run those hardware events profiling, like when we did the memory bandwidth calculations and those things, you'll get some additional columns with rocprof. The particular ones you want to pay attention to are WGR, which is work group size. This is the number of threads per block, or in AMD speak, it's the number of threads per work group. So here we got 256. LDS is the amount of local data share memory in kilobytes. And then we have the amount of scratch space. So these are spilled registers. VGPRs are the vector registers per thread, and SGPR, again, is scalar registers per wavefront. So if we plug those numbers into our occupancy calculation, so we have 52 over 50, or 50 over 52 for the vector register occupancy limit, which is going to be 96%. Scalar registers is 100%. So these guys are likely not the limiters on our occupancy. If we look at LDS is a finite resource. It's also going to put constraints on the number of wavefronts in flight. And the way you want to calculate this, so the number of work groups, so the number of blocks, CUDA blocks, that you can put on a single compute unit is going to be the amount of local data share memory that you have on that compute unit divided by the amount of local data share that's required for that work group. That's going to tell you how many work groups that compute unit can actually support. Then, if you know the number of wavefronts you have per work group, so if you take the number of threads per block, divide by 64, that'll tell you how many wavefronts that the compute unit can support for that kernel if you're using shared memory. So again, let's do that calculation, but now we've got the 64 kilobytes of LDS here, and we're going to look at the LDS usage. So here we've got about 24 kilobytes used. We've got 64 kilobytes that's available per compute unit. So that gives me 2.66 work groups that can actually run. Technically, we got to floor that, so that's two work groups that can run. There are 4 wavefronts per work groups. That's 256 threads. Remember that WGR column. 256 threads per work group, 64 threads per wavefront. That gives me 4 working groups. So the total number, if I were being generous, the total number of work groups per compute unit, the total number of wavefronts per compute unit is going to be 10 here. Out of the 40 that the MI100 can support means that the local data share usage is limiting my occupancy to 25%. So we use this as a guideline here to say, well, okay, we know we're getting bad memory bandwidth. We clearly are not going to be able to hide the fact that we have, latency and memory operations very well. So what we're going to do is kill off that local data share usage. Okay, so we know LDS usage is killing our occupancy. We suspect that low occupancy is limiting our performance. So we're going to move that 24 kilobytes of LDS to vector register usage because our vector register usage is low. We have some room to add stuff there rather than using LDS. Now, from reviewing the code, what we did is essentially look for that line where we've declared that shared memory. Said, well, what's actually in there? We know that if we wanted to just basically convert this to a bunch of scalar values that each thread has on its own, each thread is going to need 12 that should be FP64 complex values per thread. I think when we did the 32-bit calculations, of course, that'd be 12 FP32 complex values per thread. And in that case, this would only add if each vector register files, they're each 8 bytes wide. This gives us 24 vector registers per thread. So it doesn't add a whole lot. That wouldn't really kill our occupancy. And in fact, doing the, reducing the amount of shared memory we're using, this is definitely something that would improve the occupancy and hopefully improve performance. So what I've got shown here is 2 rows. We got the MI250X on the top, MI100 on the bottom. The blue bars are measurements for the original version of the code where we're using shared memory. The pink is the version of the code where we got rid of shared memory and now we're just pushing everything into vector registers. From left to right, what we're looking at is vector register usage, scalar register usage, and scratch. And I will point out at some point here, I'm going to start ignoring the MI100 stuff because this was with an older version of ROCm 4.5. But if you do have questions about that at the end, I'm happy to answer them. Now on the MI250s, we're using ROCm 5.0.2. And what we do see across both systems, the MI100 with the old version of ROCm and the new version of ROCm on the MI250X, is there's our increase in vector register usage. We go from 44 vector registers to 64. So we get 20 vector registers, a little bit better than our back of the envelope calculation. Scalar registers stay the same and our spill registers stay the same on the MI250X. On the MI100, some bizarre stuff's happening because now we're using more vector registers. There must have been some spillage because now our spill register is a little bit higher. Now let's look at runtime, the things that matter. Did this actually make a difference? The answer is a resounding yes. Again, blue is our original version with shared memory usage. Pink is using registers. We went from 2.83 milliseconds down to about 1.5 milliseconds for that one kernel. The other 2 columns here, we're looking at the total amount of memory in flight between L2 cache and HBM, that total RW column. Again, blue being our master version, pink being the new version using registers. We did kill our cache performance a little bit in making this modification. So the next step in optimization is going to be addressing that. Okay, so at this point, right, we've made the changes. We're pretty happy. We know we're getting the right results. We commit the code. We've got our profiles already, so we kind of rinse and repeat. Let's take a look at where we are. Just from that one change, the peak performance on the MI100 is now at 85% peak performance, so 919 gigs per second. On the 250Xs, we are doing better, 965, but we're at only 73% of the peak. So there's still room to grow on the MI250X GPUs. A little work to get there, though. So remember, the MI250X GPUs support fewer wavefronts in flight, so it's a little bit harder to do some of that latency or the latency hiding like we get on the MI100s. There's just a lot more wavefronts in flight on the CDNA architecture, so there's a little bit more trickery that we have to do on the 250X. Okay, I'm going to quickly go through a couple quick tips that you can do to address low L2 cache hit problems, and then I'll present some quick results here, and we'll move on to the Q&A. So we know we have some register spillage there. Sometimes it's good to have register spillage because it keeps your occupancy high. But if it is a thing you want to address, if you want to improve how the registers are used, you need to give the compiler a little bit more information. So it's highly recommended when you're writing your kernels that you use this launch bounds parameter. So by default, the compiler assumes that the maximum number of threads per work group is going to be 1024, which changes a bit how that register usage calculation is done in the compiler. So if you know at compile time what that upper bound might be, like in Dr. Comley's case, this was 256 threads per block was used for pretty much every kernel in his code. We just basically went around and dropped in this launch bound 256 decorator in front of that kernel declaration. So if you want to use it, you have your global void to indicate that you're doing a void device routine there. Then you put that launch bounds in, and then the name of your kernel. with the arguments. The other things we looked at was reordering the stencil operations. I mentioned this earlier. Usually when we're doing stencil operations, it just makes sense. If you're a mathematician or a physicist, or you've done numerical analysis before, you're like, oh, I'm just going to do the X direction, Y, then Z, then in his case, time. That's depending on how you have your memory laid out, it might not always be the optimal solution. So in our case, we just kind of experimented with a couple different ordering of these operations until we found something that hit the sweet spot in terms of getting us better runtime. And of course, if you check out Justin Chang's notes, gpuopen.com, under the HPC lab notes, you'll find some description on how this works for finite difference stencils. Great resource there. The other thing you can do is a lot of times in finite volume, finite stencil, usually in conservation law solvers in general, you'll do all these calculations and then you'll write the result to one array and you won't touch it until the very next iteration. So the deal is, if you want to bypass, normally what happens when you go to write something to memory, it's going to go through the cache and then down to HBM. If you want to bypass that cache and free up a few cache lines for other operations, you can use what are called non-temporal stores. The way that works is, like, for example, if I had f at index IDX equals sum at the end of my calculation, you could replace that with this built-in non-temporal store. The first argument is the thing you want to write to memory, and the second one is a pointer to that spot in memory that you want to write it to. Okay, now keep in mind this is something that is specific to the client, the LLVM client compiler. So, like, if you also want to run with NVCC on NVIDIA GPUs, you'll want to put this inside of some CPP preprocessing flags so that you can selectively turn this on if you're on the AMD GPUs. Okay. I'm going to very quickly go through these because we're running out of time. On the top row, let's just look there. This is the MI250X, and we're going to focus on the runtime there. Again, the blue is that original version we had. The pink was the move away from LDS and using only registers. And then as you go down through this list, it's each of these other optimizations in succession. So we've changed the stencil ordering is in teal. In green, we've set the launch bounds. And then in purple, it's using the non-temporal stores. And if you look at the L2 cache hit ratio, it basically has this sort of inverse, right? The pink is on the bottom, then we have our teal, the green. So we've very slowly improved the cache hit ratio and very slowly chipped away at the runtime there, but not really major improvements. If we look at our register usage again, pretty much register usage stayed unchanged. So our last ditch effort was to do something pretty invasive called subdomaining. Now, if you do, stencil codes, finite volume, finite difference, finite element, however, whatever you're doing in that realm of solvers, you can chunk your domain into smaller tiles, ideally into size, individual blocks that would fit into the L2 cache. It can improve the cache performance in some cases, and in this case, we found something interesting. It actually improved the register usage and did not improve the L2 cache hit ratio. So there's still some interesting things here to learn as we're doing these kinds of things, but it did bring down that runtime. So here what we're looking at, again, is that runtime on the left, L2 cache hit on the right, the total amount of data in flight in the middle. Starting with the purple is our non-temporal store, so that fastest run we had in the previous slide. And then we looked at different layouts, right? So we have, we took the 32 cube domain and broke it into 4x4x4 chunks, so smaller blocks. That purple line had improved cache hit ratio, is at the top because that problem did fit in the L2 cache. Now, if you increase the number of blocks, they get a little bit, each block itself gets a little bit smaller, does not do as well. But the most bizarre thing I found was we went back to just doing one block. So it was basically doing the whole grid. But with this new memory layout, it gave us the best runtime, but the worst cache performance. So you do find some surprising things along the way. But all these things are general strategies that we try to employ in these kinds of codes to improve that overall runtime. As I said before, this did improve a little bit of our register usage. You could see on the scratch, the spilled registers, particularly on the right side, once we went to that test layout, change that memory layout, somehow this helped the compiler make better use of those vector and scalar registers. To summarize, that's just a summary of those results there. I'll leave that there in case you guys want to peek through the slides later. But let's just recap. I'm going to repeat the motif of the day. You cannot optimize it if you don't measure it. It's always important to establish a good representative benchmark of your application. And you definitely want to dive into hotspot and events profiling with rocprof to help guide what you're doing. You want to make sure you're setting realistic goals. Remember, you got to ask yourself, are you compute or memory bound? So make sure you know your hardware, you know your code. Develop a good plan. This cannot just be done in a vacuum on its own with just the profilers. Definitely poke around at the HIP programming guide. If you check out rockum.docs.amd.com, you can find all sorts of useful information up there. And then, of course, those AMD Lab Notes blog posts walk through some really cool hands-on material to help you kind of wrap your brain around these kinds of topics. Implement your changes in small increments and verify your results at every step along the way. Rinse and repeat. Just follow that process and you'll do good. I'll leave it from here. Let's go turn it over to the Q&A.
All right, great. Thank you, Joe. Looks like you did a great job moving through all that material just about in the time we had set out and planned for it. So everyone, if you do need to drop early, this will be available on demand about an hour and a half after the call. So you can always come back and catch up on Q&A if you do need to drop now and you've got a hard stop. If you do that, please make sure that you do submit the survey before you go. One other thing, I'm going to pop up a quick poll question on your screens. You should see this in just a moment. We didn't quite get all the answers we were looking for, not necessarily the right ones, just the number that we're looking for. So that you'll see that, answer that at your leisure. So let's get into the Q&A from here. So the first one that came in, with the possibility of making a mistake by hand, why would someone estimate arithmetic intensity by hand rather than using a profiler?
I'd only recommend doing that on a system where you do not have flop counters. So if you're like on MI50s, MI25s, MI100s, there are not flop counters available, independent of what profiler you're using. So if you do want arithmetic intensity, you're going to have to hand count and try to get to as accurate as you can. The other side of it is if you just want to say, look, I'm going to pick flops per second as my metric. You can do that. Just know it might be a little challenging to figure out where that peak flops per second that you may reach is going to be.
Okay, great. Next question. What tools can people leverage to improve performance if their app is compute bound?
So you still want to stick with rocprof because you want to know, like if you're on, at least if you're on the AMD GPUs, you want to know where you're at. And just, I mentioned all those different floating point operation metrics there. If you don't know what kind of operations you're going to do, those individual flop counters will tell you what kind of things your code's spending a lot of time on. This is something that we're going to be talking a little bit about on how to leverage some of that information with the profiler, in the future, about how to optimize those compute bound codes.
Okay, excellent. Next question. Do you recommend making use of shuffle instructions for inter-thread communication rather than LDS on AMD GPUs?
It depends on how big of a reduction you're doing. I mean, if you're doing really big reductions and you get them down to where you got, a small integer multiple of wavefronts participating in the reduction, shuffle down sync operations work pretty darn well. Just keep in mind that I think there's some nuanced difference, like you can't set a mask. You can't set a thread mask with the AMD GPUs.
Okay, all clear. Everyone, keep those questions coming in. We do have Bob Robbie in the background who is answering these questions. So if we don't get to it live, we've got Bob here to get you some answers as well. So don't hesitate to send them through. Next one, did you try different work group sizes?
Yeah, we did. I think we initially tried different work group sizes when we were messing with the LDS stuff, but like the way his problem was set out was the amount of LDS was proportional to the work group size, so that didn't help initially. And then, of course, once we got to the other side, I mean, there's really we did not see a difference with his code in changing the work group size, going bigger or smaller. So, just out of, I guess, convenience or the fact that he's just done 256 threads per work group for the longest time, we just left it there because it didn't seem to make a difference here.
Okay, Okay, that makes sense. Is there a way the profiler of rocprof directly give us occupancy, like with Insight profilers?
If you are on ROCm 5.4, you can actually get what the compiler would calculate as the theoretical occupancy at compile time. There's a flag that you can send. I'll post it in the chat here or on the Q&A thing in a minute, but there's a flag that you can send to print out your SGPR, VGPR, spilled registers, LDS usage, and the number of wavefronts per compute unit that the compiler is trying to enforce. So you can get that at compile time, independent of the profiler with ROCm 5.4 or greater.
Okay, another question. How would you compare the effects of L2, L1 cache hit ratio on a GPU versus a CPU?
That's a tough question. I don't know if Bob wants to take this one.
Sure, I'll take it, but I've been surprised with the GPU. I'm so used to the CPU, but L2 and L1 does not track performance in the same way as you would see on a CPU. In fact, it may be inverse because you're launching more work groups or waves at a time. So it can be confusing relying on L2, L1. You have to recalibrate your understanding of L2, L1 and how important it is for performance. It's different than a CPU. I think you mentioned you saw that on one of your kernels. Your cache hits went down, and yet performance went up.
Yeah, and in that case, the killing off the scratch register usage increased the occupancy. So it was like, yeah, different behaviors. But yeah, I think Bob, you hit the nail on the head there. It's like if you have tons of threads, you have so much opportunity to hide the fact that you may have cache misses independent of L1, L2, which is, it's like, and that's the weird thing too, is AMD GPUs, you have a distinction between L1 and then LDS, which, on the NVIDIA GPUs, you just had shared memory and registers that weren't that granular.
Okay, great. Well, I will wait just another moment for any questions to come in. I think we've been through all that we've got now. So, Joe, Bob, thank you both very much for coming in to cover all of this. I hope everyone has found it enlightening. I don't doubt that they have. But yeah, thank you.
Yeah, thank you. And just quick plug there, Bob just dropped that compiler flag for enabling the register and occupancy stuff at compile time. So.
I think I dropped it in the team chat, so you may want to move it to the...
Oh, yeah. Ryan, could you, Zach, could you help with that?
Yeah, I'll get it in there in just a second.
Awesome, thank you.
There we go. Everyone should see that pop up in the Q&A. If you don't have that Q&A window open, open it up now, and you will see that code presently. Got it highlighting for you. All right, everyone. Well, thank you again very much for joining this Lunch and Learn. I believe there are discussions to get a third one going sometime in Q4. So keep an eye out for an invite to that and check back frequently to see if there's an update on it. As I said earlier, if you do want to come back and review any of this, I know Joe covered a ton of data in the time constraints that we all have, and some of you may have already had to drop. This call will be available on demand. You can feel free to send it out to your colleagues, come back and watch it again, review any part that you might need to check back in on. All right, everyone, thank you again. I hope you all stay well. Goodbye.